Uh, Thank you very much for the introduction. I'm very happy and it's my great honor to be here, give this talk. And I'm Pengfei Zhang from Caltech, and the title of my talk would be the branching time in SYK-like models. And to begin with, let me first thank my invaluable collaborators, Pengfei and Alexei Kitaev. Pengfei will move from Caltech to Tsinghua University next year, and this talk will be based on our paper, An Obstacle to Sub-ADS Holography for SYK-like Models. It's published in GHAP this year. So firstly, let's imagine we have some operator W applying on some local qubits. Then the Heisenberg evolution of that operator is given by taking conjugation with this evolution operator. If we expand such an evolution in terms of time t, it takes the form of taking commutator between the Hamiltonian and the W operator. So as time going on, this tells us the operator W will become more and more complicated. And if we really want to ask how complicated this operator is, we can take the commutator between this W operator and some other operator V. So for example, let's consider taking the commutator and then choose to take the norm square and take the expectation value. So this is defined as the auto time order commutator or the retarded OTOC. So on the other hand, we can also expand such a commutator square in terms of simple correlators, like these simple 4-point functions. In particular, there will be contributions containing the time sequence, which is T0, T0, or 0T0T, which is called auto time order correlator. So more generally, we can introduce 4 different operators with 4 different complex time. So here, this theta is a complex time, where this real part of the theta is the imaginary time, and the imaginary part of the theta is the real time. So it's a very interesting convention. So for the normal auto time order correlator, is defined to be order in the imaginary time sequence. So on the other hand, for this retarded OTOC, we choose tau 1 equals to tau 3 and tau 2 equals to tau 4. So generally, for 0+1 dimensional larger models, which is will be our main focus today, it takes the auto time order correlator or the retarded OTOC takes the following form. So in the early time behavior, if t is 0, if we choose the W and B operator just commute between each other, then this retarded OTOC will be 0. So in the long time limit, the W operator will scramble into the full system, and there will be some saturation value. So for this early time behavior, it's really very similar to what we are experiencing in this world. It's a pandemic. So the initial operator is like a patient, and the calculating the retarded OTOC is like asking how many people are infected. So they know this early time behavior is the exponential behavior, and this exponent motivated by its similarity comparing to a semi-classical chaos where 2 nearest neighbor trajectory will deviate from each other with some exponential factor. So this is known as a classical Lyapunov exponent. And here we define this exponent for the retarded OTOC or this normal auto time order correlator as a quantum Lyapunov exponent. And it is known by this paper by Madasena, Shank, and Stanford that general quantum system, the quantum Lyapunov exponent will have an upper bound by this 2 pi over beta. And it is also known that such a bound is saturated by a black hole, by holographic system that is due to semi-classical black holes. So generally, computing the auto time order correlator is not so easy, in particular for strongly interacting quantum systems. So fortunately, there is a solvable model for the information scrambling that is called the SYK-like model. So such a model describes the random interacting Majorana fermions with this ji1 to the iq, which is just the random interaction parameter. And there is a 0 expectation value for the random parameter, and there is some variance. So by choosing such a variance, we will get a model that is solvable with a well-defined larger limit. For example, the self-energy for the 2-point function is known to be a Mellon diagram, which is proportional to Green's function to the q-1's power. So it is also known that in the low temperature limit, the effective mode of the SYK model is so-called reparametrization mode, which is due to an emergent conformal symmetry at the low temperature limit. So the Green's function can do a reparametrization, which gives such a transformation. one can further ask, what is a soft action for the SYK model at the low temperature limit? So to the leading order of the 1 over beta J expansion, it is known that such an action is called a Schwarzen action. One can do just the independent calculation from a gravity side. And from gravity side, we are using something called a Jackie-Tedman gravity, which is a dilaton gravity with a linear dilaton potential. So in the bulk, this first term is defined in the bulk, and in the bulk, this dilaton field is like a Lagrange multiplier, which is linear. So we can integrate out this dilaton field directly, and it's just fixed r plus 2 equals 0. So we have r equals -2, and this will fix all the degree of freedom in the bulk. As a result, only dynamical degree of freedom for this gravity model only comes from the fluctuating of the boundary curve. And if we work out the details and choosing some boundary condition and renormalization condition, then the action of the boundary term, the second term, will directly take the form of the Schwarzen action. So this tells us SYK model to the leading order of 1 over beta J expansion has some gravity description. And SYK model is maximal chaotic at this leading order. So then it's very natural to ask what happens to the next order. So basically in this previous works, it is known that to the next order of the 1 over beta J expansion, there are basically two effects. So one effect is that there is a correction of the bulk local action. So this is mostly easy formulated in terms of a gravity theory, where we just need to change the action a little bit by adding the term that is proportional to a phi square, which is quadratic in terms of a dilaton field. So since this term is quadratic now, so it's no longer linear, and the dilaton field is no longer a Lagrange multiplier, so it will contribute to some non-trivial bulk dynamics. So instead of just integrating out the phi to impose some simple r equals to -2 condition, now we have some interesting bulk dynamics. And if we integrate out the bulk, it will lead to some non-local action on the boundary. So to really see such a contribution in subleading, for example, we can look at the thermodynamical property. For example, here, this thermal entropy is given by such an expansion. So this first term is a topological term. The second term is proportional to the temperature, which is a contribution from the Schwarzen action. And this third term is a contribution from this new part of the bulk action. So there is another effect to the subleading order of this SYK model, which says instead of having a bulk local action, there will also be effects saying the gravity picture is no longer valid. So this is because the Lyapunov exponent at this subleading order will get the correction, this 1 minus 1 over beta J correction, which says it's no longer maximal chaotic. So there should be some non-local bulk effect, which makes this Lyapunov exponent smaller. So we can ask what is the ratio between these two different effects. Basically, we can take the ratio between the variation of this Lyapunov exponent over the variation of the specific key. So in the original SYK model, in the low temperature limit, copying some papers copying some equations from these papers, we can work out this ratio. So which is proportional to the derivative of the conformal kernel over the derivative of the retarded kernel. So it is also defined in the previous paper by Pengfei and Alexei that the derivative of the retarded kernel is called branching time. So now let's imagine so in the original SYK model, so we can just work out what is the value for this derivative of the conformal kernel, what is the value for the branching time, and they are just some constant which is of order 1. So in the original SYK model, these two effects appears at the same order, in fact, compete between each other. So there will be an important decoherence effect, which makes this Lyapunov exponent smaller than the 1 over beta, than 2 pi over beta at this subleading order. And one can imagine we are interested in finding some other model. Maybe we want to modify the SYK model a little bit and ask whether we can get an interesting model with non-trivial bulk dynamics, but at the same time, the system can still be described by a local bulk action. So for this, one idea is that whether we can come up with some theory where we can have a very large branching time, then this ratio will be a surprise. So this ratio will be surprise. And so let's go to turn to some literature and ask what we usually do to generalize the SYK model. So for example, to generalize the SYK model, one possible route is to add some symmetry. For example, the simplest case, we can add the U1 charge conservation. Then instead of a Majorana fermion, we have some complex fermion described by this C or C dagger. And there is other probability of let's introducing different SYK models. For example, we have this chi fermions, which is the SYK4 model, and have this precise fermion, it's a SYK2 model. Then we can couple them using some random hopping, and there can be some interesting transitions or crossovers for such models. It's also possible to introduce some higher dimensional generalization of the original SYK model. Basically, we can imagine there is a site index, and on each site, there is a SYK model, and we can introduce pair hopping, a random pair hopping between nearest neighbor sites. So there will be a higher dimensional models. So in all these generalizations, we can, in fact, if we focus on the early time behavior of the auto time model correlator, we can write it in terms of a ladder diagram. So in the original SYK4 model, this vexy line, or what we call the Rungs function, is in fact, for example, in the SYK4 model, it's a pair of the fermion-Grun's function. However, in more general cases, we can assume there is some general Rungs function with no simple relation to the fermion-Grun's function. So, and there is another difference for the SYK-like models comparing to the original SYK model is that there is an additional flavor index, A. So for example, such A can be the particle or hole in the original this complex SYK form. This A can be the label for chi fermion or precise fermion for the second case, or this A can be just the site index X. So in all these examples, there is also a symmetry where if we have two A particles coming into the system, it will be scattered only into a pair of C particle or pair of B particles. So there is kind of a pair flavor conservation symmetry for this type of diagrams. So we use this type of diagrams to define so-called fermionic SYK-like models. So whenever we have such a ladder diagram, we can translate it into a self-consistent equation defining some retarded kernel. And here the retarded kernel is given by the retarded Grun's function times the advanced Grun's function at time this vexy line. So this vexy line is a R function, which we call the Rungs function. And in these general cases, we can imagine there should be some level A for the retarded Grun's function and the advanced Grun's function. And this Rungs function is also a matrix in this AB index. So then we have the retarded kernel. We can use a very traditional way to determine the Lyapunov exponent given by the eigenvalue equals to 1, and the branching time is given by the derivative of the retarded kernel. And the auto time model correlator also takes the form of two fermions fusing into a single collective mode called scrambling, and then such a scrambling split into another pair of fermions. In particular, the scrambling has a very interesting Grun's function, which is exponential in time. So this factor. So it's very different from a more traditional collective excitation, which decays in time. So, so this is a definition of the SYK-like models. So what we really want to answer is whether we can construct model SYK-like model with a very large branching time. However, before answering the question, let's take a detour. So at the end of the day, we will find such a study will be very useful for proving the relation for the branching time. So as mentioned in the last slide, the auto time order correlator generally takes the form of summation or ladder diagrams. So then we can define the contribution with n vector line as Fn. So it's a summation or Fn. We can view such a summation or Fn as defining some probability distribution, but it's in fact not really a real probability distribution because this Fn is cannot be shown to be positive. So it's really like a pseudo probability distribution. And we can use such a pseudo probability distribution to study what is the statistics of the number of rungs. Then to determine the cumulance of the number of rungs, we can define some called a generating function, which is just a summation over n with e to the mu n. And such a generating function is easy to compute because the important observation is that this e to the mu n factor just tell us every time we see a new vector line, we need to attach additional e to the mu factor. So as a result, this generating function will satisfy a similar equation comparing to the original OTOC. So it will satisfy such an equation with this additional e to the mu factor. So we know the original OTOC will have some exponent, will have some exponential behavior in the long time limit. So similarly, this generating function has also a similar form, so which is the exponential factor, and this exponential factor originally corresponds to the quantum Lyapunov exponent, now gets some modification. So now it's depend on mu. And to determine the dependence of mu, we have this equation, which is the analog for the equation that we determine the quantum Lyapunov exponent. And for example, if we are really interested in the expectation value of number of rungs, we can take the logarithmic derivative of the generating function. And the main contribution in the long time limit is from this exponent, which is linear in time t. This t is the total evolution time. And we can find another factor, which is given by the derivative of this quantum Lyapunov exponent. So one can further show that such a definition is consistent with the definition of the retarded kernel, which gives this derivative of the Lyapunov exponent is just 1 over branching time. So the expectation value of number of rungs is just the total evolution time over the branching time. So what do we learn from this simple calculation? So the first thing is that the branching time can be computed by adding this e to the mu factor and ask what is the Lyapunov exponent and take the derivative of the Lyapunov exponent with respect to mu. So this is useful because in the literature, there are many different methods to approximately compute the quantum Lyapunov exponent. Now having this relation, we can immediately translate the approximation for the quantum Lyapunov exponent into an approximation of the branching time. So such a calculation also tells us the branching time has a diagrammatic interpretation. So the branching time gives the so the total evolution time over the branching time will be equal to the expectation of a number of rungs. Then this tells us the branching time is just the average separation between the nearest neighbor rungs. So this is the interpretation of the branching time. We can also, following this lower solid line for the fermion, this fermion line, and it's like the main branch of the tree. And every time we see a new vector line, it's like adding a new sub-branch. So such a calculation also takes the form of a stability analysis. So for example, the original calculation, we add this e to the mu factor to the retarded kernel. However, it can be viewed as some artificial modification for the retarded kernel. And we are asking whether the Lyapunov exponent is sensitive with respect to this new factor. So more generally, we can imagine some more realistic modification of the system. For example, we can consider adding some interactions to the system. We can imagine we can change the temperature of the system, and then there will be a change of the retarded kernel. So more generally, we can determine the change of the Lyapunov exponent, which can be shown to be proportional to 1 hour branching time. So branching time really characterizes how stable the quantum Lyapunov exponent is. So as a very special cases, we can ask what is the behavior of the system, what is the expression of the Lyapunov exponent near maximal chaos. So one can show that near maximal chaos, the Lyapunov exponent, the correction of the Lyapunov exponent also proportional to 1 hour branching time. So such a calculation also validates our requirement of having large branching time if we want to have some interesting holographic system. So previous discussion is only for using in the previous discussion we use the explicit formula for the SYK model. However, in this discussion we just assume the ladder diagram structure. So this formula is much more general. So this simple calculation also gives us an alternative derivation for so-called ladder identity. So the ladder identity original derived in the previous work by Pengfei and Alexei is a relation between this quantum Lyapunov exponent, this C, which is the coefficient of the OTOC, and this branching time. So to derive an equation containing this factor C, we need some either some inhomogeneous equation or some nonlinear equation for the auto time order correlator. So here, let's consider we attach two auto time order correlator together. So the left-hand side is some retarded auto time order correlator, and the right-hand side is a normal auto. So we choose them to be different because some requirements from a Keldysh contour. And then attaching them together, and we need to add some rank function or vexy line in between. So so what's the result when we attach them? So there will be a diagram with a single vexy line, and that vexy line will be just this blue vexy line. So there will also be some contribution with two vexy lines. So then this blue vexy line can either be the left one or can be the right-hand side one. So as a result, there will be an additional factor of 2 for this F2 contribution. So similarly, for general contribution proportional to Fn, there will be additional factor of n. So after attaching the retarded OTOC with the normal OTOC, we get such a formula, which is the summation over n times Fn. So such a summation is just what we have computed in the previous slides. So it's proportional to the expectation value of number of rungs, which is just the total evolution time over the branching time. So using that formula, plug into this equation, we immediately get this relation for the Lyapunov exponent, the coefficient of the OTOC, and this branching time. So finally, let's come back to our first question of whether we can construct some SYK-like models where we can study the auto time order correlator and the effect of information scrambling explicitly. And we still hope that such models have very large branching time. So we have tested many different models. Unfortunately, finally, we come up with a no-go theorem. So we prove the bound that for fermionic SYK-like models, or diagrammatically, this just means for fermionic model with such a ladder diagram for the auto time order correlator, the branching time will be bounded by 2 over the Lyapunov exponent. So there are several steps for this proof. The first step is just write out the eigenequation for the generating function. So here we have added this e to the mu factor for this retarded kernel. So after adding it, you can ask what is the explicit dependence of mu. So it will appear here in this factor, but in addition, it also appears in terms of the dependence of the Lyapunov exponent. So there will be a dependence of mu in the argument of the retarded Green's function and the argument of the advanced Green's function. Then using this eigenequation, we can use the Feynman-Hammer theorem to take the derivative with respect to mu and set mu goes to 0. The Feynman-Hammer theorem says every time when we want to take the derivative, we just need to take the derivative with respect to explicit factor. So there will be a derivative with respect to this factor and also factor of the retired Green's function and the advanced Green's function. So one can derive a relation that the branching time can be written in terms of the expectation value of the phase binding. So this phi is in fact the phase of the retired Green's function. And this d phi d omega is the phase binding of the retired Green's function. So then if we want to really determine some bound for the branching time, we just need to find some bound for the phase binding of the retired Green's function. So the main observation is that this retired Green's function with additional minus sign is in fact defined as an analytical function from upper plane to upper plane. So on the other hand, upper plane is equivalent to a unit disk. So we can construct a composite function which map from a unit disk to another unit disk. So for such a function on a unit disk, so we can use the so-called Schwarz lemma, which bound the derivative of such an analytical function. So applying that Schwarz lemma to this composite function, we immediately find such a bound for the phase binding. So finally, using this bound for the phase binding, we can derive such a bound for the branching time. So let me ask a few discussions. Firstly, we can ask what happens in original SYK model in the low temperature limit. So there will be some concrete formula we can write out, which says if we take Q larger than 2 and smaller than infinity, this branching time times the Lyapunov exponent will be larger than 0 and smaller than 3/2. In particular, for example, for Q equals to 4, it will take the value of 2/3, and for Q goes to infinity, it takes the value of 3/2. So in the original SYK model, we know this result shows it's consistent with our bound and it's no longer saturates the bound. So in fact, we have some arguments saying we do not expect there will be model saturating the bound. The reason is that if we ask what is the phase of the retired Green's function at omega goes to plus infinity minus the omega goes to minus infinity, so it will be fixed. So such a relation serves as a sum rule for the phase binding of the retired Green's function. So as a result, such a bound for the phase binding will not be saturated for all the frequency omega. So generally, we'll expect the branching time will be smaller than 2 over the Lyapunov exponent. So although in previous discussions, I haven't write out all the flavor index A explicitly, in fact, this can be done very easily by adding all the levels. So this bound works for general SYK-like SYK chain models or SYK model with multi-flavors. So this model is also interesting for both the weakly interacting limit and the strongly interacting limit. So for example, in weakly interacting limit, one can imagine that both the Lyapunov exponent and the inverse of the branching time will be proportional to the interaction strength, which is like J in the SYK model. So in the strongly interacting limit, the Lyapunov exponent and the 1 over branching time will be of the thermal scale, which is 1 over beta. So in both cases, from this simple argument, we know the branching time times the Lyapunov exponent will always be of the order 1. So our bound saying their product is smaller than 2 is always meaningful. So in fact, in weakly interaction systems, we can go further by assuming the retired Green's function takes the form of some quasiparticle. So this capital gamma is the decay rate of the system. Then we can write out the eigenequation for the retired kernel after adding this e to the mu factor directly in the time domain. So it will take the form of the Schrödinger equation with the first term, which is the derivative of the time, is like the derivative in the spatial direction in the one-dimensional Schrödinger equation, which is a kinetic term. So this And this second term, which is proportional to the Rungs function R, is like the potential energy in the scattering problem. And there is the last term is like the total energy of the system. Now we can again using the Feynman-Hartmann theorem to derive the relation of a branching time to the potential energy. So the branching time is the derivative of the Lyapunov exponent. So we can take the derivative for this total energy with respect to this mu. Then using the Feynman-Hartmann theorem, this tells us such a derivative will give you the potential energy. So this part. So we can show the potential energy is just proportional to 1 over branching time. So in this special case, there is a very simple way to derive the bound for the branching time. So that is, we know the total energy will be larger or smaller than the potential energy. The reason is it's a summation over the kinetic energy and the potential energy. However, the kinetic energy is the expectation value of some operator that is positive semi-definite. So expectation value will be larger or equal to 0. So as a result, the total energy will be larger or equals to the potential energy. And we will, using these formulas, we will directly give such a bound for the branching time, which is smaller than 2 over Lyapunov exponent plus this capital gamma, which is the decay rate for the quasiparticle. So comparing to the previous result, we find instead of a 2 over Lyapunov exponent, now we find this 2 over Lyapunov exponent plus the capital gamma. So this is mainly because when we assuming the Green's function takes the following form, which have a simple pole plus some decay rate, then we have changed the analytical domain of the retarded Green's function. Now the retarded Green's function is the analytic not only on the upper plane, it's also analytic if the imaginary part of the omega is larger than minus I gamma over 2. So as a result, this extends the analytical domain of the retarded Green's function. As a result, it will lead to some tighter bound of the branching time. So since it's just a one-dimensional scattering problem, we also have many ways to do the approximations. For example, let's take the most crude approximation, where we just approximate such a Rungs function by some delta function. So in this case, we have a particle in the delta potential. It's very easy to solve. We can compute the spectral and everything we want to do. And we find there is an approximate relation between the Lyapunov exponent, the branching time, and this quasiparticle decay rate. So such a relation is in fact very interesting. So why it's interesting? This mainly because we can compare such a result for the weakly interacting system to the near maximal chaos. For weakly interacting system, so here the sign of this one branching time is positive. However, in the case where we near the maximal chaos, we find the contribution of the one branching time has a negative sign. So this implies there are in fact a different mechanism for the information scrambling. For this weakly interacting system, the Lyapunov exponent got a positive contribution from the branching. So the branching will lead to the information scrambling. However, near maximal chaos, there is a different mechanism where it's covered by some coherent process, like coherent scrambling, like gravitons. So if you have some branching, it will suppress the scrambling. So in the early talk by Alexei in 2018 at KITP, there is a very interesting analog with having breakfast. So like sometimes we want to mix honey and water, and sometimes we want to relax ourselves, we just put honey into water. And then they will mix, but basically due to some dissipative process, like the diffusion process, where the molecule of the honey will diffuse into the molecule of water. So on the other hand, sometimes we are in a hurry and we mix the honey and water, we just use a spoon to create some collecting mode. And at this time, the honey and water mix more efficiently. So this is like we create some coherent mode to scramble the quantum information. So, so finally, there is a summary of this talk. So in this talk, I explained that there will be some inevitable decoherence effect in the SYK-like models. In particular, we proved there's a bound for the branching time, which is given by the Lyapunov exponent times the branching time will be smaller than 2. We also show that there are 2 different mechanisms for the information scrambling near the maximal chaotic cases. The information scrambling will be dominated by the coherent scrambling, where the branching will take the minus sign. So in weakly interacting systems, the information scrambling is due to this branching. So there will be several interesting things in the future. In particular, since we have proved that the fermionic SYK-like models cannot have very large branching time. Now, if we really want to have some model with large branching time, maybe have some interesting local bulk dynamics, we need to go beyond the SYK-like models. So for example, we can consider about matrix models, which is motivated by a higher dimensional super Yang-Mills theory. However, such a model is usually hard. And we can construct some condensed matter flavor model. For example, we can consider adding different SYK models together and add some Hubbard interaction between them. So for the static SYK case, it's relatively hard. However, if we consider the Brownian version, the Brownian SYK plus some Hubbard interaction, one can do the calculation. And we show that we have some preliminary results showing that the branching time times the Lyapunov exponent plus the capital gamma, which is quasiparticle decay rate, will slightly violate this bound. So there are also probability of considering models with bosons because our proof is only for fermionic models. So we can ask what about models with bosons. So for example, we can ask about the supersymmetric SYK model. Although we do not have a proof for that, if we do the calculation in the low temperature limit, we will find the branching time is also of the order 1. So it's really an open question that what type of model we should look for in the future if we really want to have a very large branching time. Okay, thanks for your attention. So this is the end of my talk. So any questions?
Just a
Can I ask a question?
Hi, sorry.
Oh, hi, Pengfei. So the SYK plus Hubbard, what does that mean? Because SYK is already interaction between fermion, Hubbard is also interaction between fermion, so I'm not quite sure.
Oh, yeah. Let me briefly explain this in more details. So like in SYK model contains certain Lagrange structure. So we can have ladder diagrams and solve this model in a very analytical way. We write ladder diagrams. However, if we let's consider we have a full copy of the SYK model, and within each copy there will be a SYK interaction. And then at each site, instead of this I label, there will be an additional label like A. A is from 1 to 4. And then we can add additional Hubbard-like interaction, which is U chi1 to chi4. So such a new interaction will change the Lagrange structure of the system. And there is no simple like ladder diagrams for the system. So I just mean if there is simple ladder diagram structure, as we have shown here, there will be a bound for the branching time. However, if you add some term which breaks such a simple ladder diagram structure, it can be interesting. Then in particular, if we, instead of using the static SYK interaction, we use a Brownian SYK interaction, then this problem can be solved, using some initial state and some EPR pair, and there is some evolution, and it can be reduced to a problem with few qubits, and you can do all the calculation there just explicitly and get a very interesting result. And the result shows this will violate this bound for the branching time a little bit.
Okay, thanks.
Just a small question. What is the value of this capital C, or what is the definition of capital C on this slide?
Oh, yeah. the capital C is a coefficient, is this factor also auto time order correlator. So it's a coefficient. Oh, sorry. Maybe I should mention for this coefficient C appearing in some equations. I also take some normalization for this y function, this vertex function. So otherwise there will be some arbitrariness. So arbitrariness. Right.
I think there's another class of SYK-like models, which is you take the Hamiltonian of SYK and add to it the Hamiltonian squared with some coefficient. And you can do it in a way that breaks this melonic expansion that these theories have. I just want to make sure I understood correctly that the bound that you're talking about wouldn't apply in that case, right? If you break the melonic expansion.
Sorry, break what expansion?
The melonic large N expansion.
Oh, yeah. If you break this as like a large expansion or ladder diagram, the bound will not work. Right. So that's right. Yeah. Right. That's also yeah. That's also a very interesting question of whether. Yeah. Basically, here what we propose is just some simple example of breaking this SYK-like ladder diagram large N expansion. There will be many different ways of breaking this larger limit. Yeah, it's also very interesting to ask what happens in that models. Yeah.
I think I don't quite understand the picture about coherent scrambling and the picture about the breakfast adding honey in the water. Could you explain again?
Okay. So it's like the main contribution is from a dissipative process or a decoherence effect, or is from some collecting mode that is coherent. So for example, there are near maximal Kells, you can basically imagine that the main contribution is like the boundary graviton, so like the shock wave, and as a result, if you add something else to this boundary graviton system, so it will make the information scrambling less efficient. So here, however, in weakly interacting system, there is nothing like the boundary graviton. So you can just use some scattering between quasiparticles, some like dissipative process to lead to the information scrambling. So in this case, it's dominated by this branching. So as an analog to this breakfast case, so in this if you put the honey into water and just wait, it will be dominated by the dissipation process, right? It's like the diffusion. Diffusion is something will create some entropy. So it's like a dissipative process. And on the other hand, you can use a spoon to create a collecting mode. So this is like creating some boundary graviton. So this is more efficient than just wait there. So if you just wait, you need some dissipation, like dissipative, like diffusion, then the honey and water can mix. So, but if you create some collecting mode, this is like creating some boundary gravitons, and there will be shock wave. So it will mix the honey and water very efficiently. Like when have the shock wave, the SYK model is like maximal chaotic.
How do I understand that branching will suppress the scrambling from the later picture?
I was saying how to understand it from this cup or from the original?
From the honey.
So sorry, I can't really hear you. Can you say that again?
But it looks like to me, for the second case, when you just disturb the water with a spoon, like diffusion also helps to scramble. I don't see like a suppression factor from the. Right. Yeah, I understand your concern, right? But there will be other. But there can be other type of dissipation appearing in this system, like maybe there will be some friction between your spoon and the cup. Then this will make the mixing less efficient. So there can be different mechanisms for having like dissipation. Okay, thank you.
Yeah, I have a question for your equation about the kernel acting on the OTOC. Can you turn to that page?
Okay, okay. Maybe this one or
yeah, this one. Yeah. So in last line you said the OTOC in the form of two function of gamma times exponential t. So that is an answer for the self-consistent equation, or you can basically prove that you must have that form from your self-consistent equation.
Yeah, it's a good question. Okay, okay. So basically, firstly, if we want to solve such a self-consistent equation, we want to ask what is the eigenvalue and eigenspectral of the retarded kernel, right? Then we need to label a different eigenvalue and eigenequations. And eigenfunctions. So for this retarded kernel, it only depending on this time difference. So it's only depending on the time difference between 1, 3, 4, 2, and 3, 4. So as a result, if we do a time translation, there is a time translation symmetry for this retarded kernel. As a result, this eigenfunction it will be labeled by a central mass frequency. So this alpha is basically a central mass frequency part, and this is like the eigenfunction in the relative coordinate between T1 and T2. Then since generally the eigenfunction takes the following form, so the auto time order correlator, if you apply this retarded kernel from left-hand side, and then this dependence on first two time for the OTOC will be this function. So this explains the half of this result, this exponent plus this YR function. Then you can do another thing where you can define something like advanced kernel, which applies on this auto time order correlator from the right hand side. So you can imagine there will be some similar equation where we write OTOC applying on this Ka equals to OTOC. Then in that equation, you can do similar analysis, giving you another function called YA. So this means such a formula for the OTOC is in fact a consequence of such a ladder diagram. So the only assumption here is that the solution for this is not degenerate. So we do not have two modes for this. We do not have two modes with the same quantum Lyapunov exponent. So in that case, there will be a further summation over two modes. But if we only have a single mode, it's like a single scrambling that dominate in the information scrambling. So this will be the result.
Oh yeah. But my question is like, what about the exponential kappa k? Kappa t? It seems like it's not necessary to have the exponential part, right? That is an assumption for the scrambler, right?
Oh, sorry. This is in fact this kappa is a central mass frequency. It's like an imaginary frequency, but it's a central mass frequency. So this retarded kernel, the eigenfunction of the retarded kernel, because the retarded kernel is time translation invariant, so the eigenfunction will be labeled by some central mass frequency. However, in this case, the scrambling means the central mass frequency is in fact some imaginary frequency. So this alpha is like an imaginary central mass frequency, right? So then for this minus alpha, for the solution of minus alpha, we need to choose what alpha is, and to choose this. The idea is to solve the eigenvalue of the retarded kernel equals to 1. After solving that, this gives you alpha, like alpha is minus kappa. So this leads to the exponential factor here. So this exponential factor here is just the exponential factor here. So the imaginary frequency of the eigenfunction.
Okay, let's thank Pengfei.